Yeah, so I'm going to talk about wave drag and wave thrust phenomena. And an example which highlights quite nicely what I'll talk about is this, this paper that won Ig Nobel Prize recently, and it was a JFM paper, talking about how ducklings are finding the optimum spacing in their mother's wake. So this is showing both wave drag and wave thrust because the mother duck, as she swims, she's creating a wake, and that's costing her energy. So that's associated with wave drag. And the ducklings, they're swimming in her wake, and they're getting a boost from surfing in her waves. So that's a wave thrust example. And this cartoon sort of illustrates what I'm talking about. So basically, if the ducklings are in the wrong positioning, they're going to be swimming against surface gradients, so they're going to get pushed backwards. And if they're swimming in the right positioning, they're going to be swimming on positive gradients, and they'll get pushed forwards, and that helps them. Okay, so yeah, so I'll talk, give two examples on wave drag phenomena. Basically, first of all, looking at how the shape of the object moving through water affects its drag, its wave drag. And secondly, what happens when the depth of the water changes, how that changes the wave drag. And then secondly, I'll talk about wave thrust phenomena. So I'll talk about this, this phenomenon called gunnel bobbing, which is shown in this video, which is a mechanism by which you can jump on a canoe to push it forwards. And I'll talk a little bit about the same idea at much smaller scales, which is related to how insects move around using capillary waves. So please feel free to ask questions anytime. No. That's a friend and collaborator of mine in front of Trinity College, Cambridge, actually. Okay, so wave drag. So for those who haven't come across wave drag before, I'll just mention a little bit about the idea. So it's kind of summarized quite nicely by this plot. So on the x-axis, you have the Froude number, which is basically just the speed of the object divided by square root gravity times the length of the object. So we can think of this as dimensionless speed, and this is dimensionless drag. So that is drag divided by the inertia, so rho u squared L squared. Rho is the density of the water. Okay, so basically, this drag has a characteristic peak around Froude number half, both according to theory and observed in experiments. And so what's basically happening is if the Froude number is very small, you create waves which are very short wavelength. If the Froude number is very large, you create long wavelengths. You'll see that behind like a speedboat. You get these big long waves. And essentially, there's some sort of spot in the middle, which is around Froude number half, where you get a resonance between the boat length and the wavelength. And that's associated with a peak in this wave drag. Okay, so a few years ago when I was doing a postdoc in Paris, I was doing some experiments in a tow tank. So this is a video showing a model boat being pulled through a sort of small pool, a 6-meter long pool. As the boat is pulled through the water, you simultaneously measure the drag force. Essentially, I was interested in understanding what determines the optimum shape of the boat, and in particular, if you can create a family of curves which somehow capture asymmetry. So the idea being that so 1 is a perfectly symmetric boat front to back, and then as you progress through to 5, you get more and more asymmetry. So I'll show you the wave drag plotted as a function of Froude number. So these are experimental measurements. But the plot is flipped left to right. So the idea being that these boats are like these boats moving in the other direction. So as I cycle through the shapes, you see this pattern that basically epsilon positive just means the boats are rounded at the front, and epsilon negatives means that they're more pointed at the front. So as the boats become more rounded at the front, the wave drag gets worse, and as they become more pointed at the front, the wave drag gets better. So that's the kind of idea. The problem is, so you can write down a theoretical calculation for the wave drag. It was first derived by Mitchell in 1898, and it's based on slender body theory. So it's a potential flow. You take a Fourier transform of the boat shape, and you get this curve, which is this very beautiful curve. You can see these kind of oscillations associated with the fact that you're taking a Fourier transform of a finite object. Okay, the problem with this theory is that it cannot tell the difference between forward and backward motion. Okay, so there's this paradox that takes place. So as I cycle through the different shapes, you see that, okay, this shape has a different Fourier transform from this shape, but you can't tell whether it's moving backwards or forwards. So that's the idea. So there's a paradox here, and we want to try and address it. So where does this paradox come from? Basically, so you can write down the Euler equations and boundary conditions. So if F here is the shape of the boat, then this is an impermeability condition. This is the kinematic condition on the free surface, dynamic condition, and a far field condition. And the problem, so you can work through this in your heads quickly. If you make the transformation, u goes to minus u, you get the same equations. So that's the problem, basically. You switch the direction of the velocity, and everything stays the same. Can anyone spot how you could add a term to these equations to fix that? Can you think of a term that you could add to the Euler equations that would break the symmetry? Yeah, viscosity, for example. Any other term? So you could add viscosity. You could also add time dependence. Okay, so both would do it. Yeah. So yeah, you probably didn't see that the time term was missing. But so either of those terms would now break the symmetry. And that's essentially what's going on. So really, what's happening with these shapes is that there's a boundary layer, there's a turbulent boundary layer. So both viscosity and time dependence are important. You can use numerical simulations, for example, to calculate what that boundary layer looks like. And then so what we thought about when we were modeling this a few years ago is we thought, well, okay, potential flow theory only really applies up until the region in which viscosity is important. So if you go inside that region, you shouldn't really be using potential flow theory anymore. And so what you can do is you can, instead of taking a Fourier transform of the shape, take a Fourier transform of the shape plus its boundary layer. And if you do that, you recover the trend that we saw in the experiments. Essentially, that these boats have larger wave drag, and these boats have smaller wave drag. So that's shown quite nicely by these simulations. So these are simulations I did in OpenFoam, which is kind of like it's a CFD tool. And so you take these asymmetric boats, you pull them through a water surface, and you can calculate the wave field. And quite clearly, you can see that this boat is generating a much bigger wave field than this boat. Just sort of what you'd expect, right? But this is just shown using a numerical simulation. And likewise, you can calculate the drag as a function of time in these simulations. And you see that over some time, the blue curve loses. It's got more drag. So blue curve corresponds to positive asymmetry. So this one. So are there any questions about that? No? Yeah. Yeah, that's interesting. I honestly have no idea what's going on at early times. But yeah, you could make an argument that there's an early time at which it might be better to be with this boat, but that time doesn't last for very long. So, yeah. Okay, so the second thing I wanted to talk about was water depth. So this is kind of motivated by rowing races, and essentially if you look at different rowing races around the world, different Olympic venues, for example, you see that the water depth is quite different. So in Rio de Janeiro, you have a mean depth of 2.8 meters and a maximum depth of 4.3. If you compare that to the length of an 8 rowing boat, you can see that you can be in a limit where the depth of the water is much smaller than the length of the boat. So you need to start taking into account the shallowness, essentially. Okay, so this is work that was done by an old master's student I was supervising called Rafid Bendimarad, who's now, he was doing a PhD in Cornell. He might have finished now, I'm not sure. So Rafid did these experiments in the same tow tank in Paris, but he went and changed the depth of the water, okay? So pulling the boats through the water, but now decreasing the water level. So you introduce a new parameter, h, which is the depth of the water. Okay, so I'm going to show you the drag curves here, but they're slightly different to the drag curves I was showing you before. So that first of all, they're normalized differently. So instead of normalizing by inertia, I'm now normalizing by rho GL cubed, which you can think of as sort of the mass of the boat. I should say the weight of the boat. Yeah, so there's a slightly different normalization. The key thing to notice is that as speed goes up, drag keeps going up, which is what you would expect. The faster you're going, the more force you would expect. So just pay attention to that. And then the second thing to pay attention to is the fact that there's now 2 Froude numbers. So there's the classical Froude number, the length-based Froude number, but there's now also the depth-based Froude number. So this is the Froude number measured with respect to the water depth instead of the boat length. Okay. You do see it. It's just not, because you're not dividing by u squared anymore. So basically you see a change in slope. Yeah. So if you divided this by u squared, you would see that peak. So this was for depth over length, a bit larger than 1. A bit larger than 1, you're basically in the deep water regime, and you don't care about the depth of the water. It's just, you can think of it as infinitely deep. What happens if you go shallower is you start to see this strange thing happening, which is that you develop a bump in the drag. So essentially you get like a little bit extra drag when you're close to when the depth-based Froude number is 1. So when you're close to FRH1, you get a little increase in drag, and then at slightly larger velocities you get a little bit of a decrease. Okay, so if you keep going shallower, this accentuates even more, and you develop a stationary point. So these are experimental measurements, and you really see this turning point in the data. And the reason why that is because you're picking up a resonance with the shallow water wave speed. It's a new resonance, basically. So now you're capturing, as the water is very shallow, if you travel close to the shallow water wave speed, which is square root GH, then you pick up this resonance, and that gives you added drag. Okay, the interesting thing about this stationary point is now, if you take a constant value on the y-axis, you can get multiple solutions. So that's shown by this hysteresis curve. So imagine if you are slowly ramping up your forcing. So I slowly increase R. What's going to happen is I'm going to increase my speed. I'm going to travel up this curve. But at some point, I reach a turning point. And if I keep increasing my speed, I'm going to jump to a different solution. Okay? You can actually prove that this intermediate solution is unstable because of the negative slope. Okay, what happens then if you decrease the forcing? So if you decrease R, you would now return on a different solution branch. And so you would have this hysteresis effect. So we thought, we thought this was interesting from the rowing application because you can sort of imagine yourself in a rowing race with a variable depth. So let's say I choose a somewhat idealistic rowing race, which has a sinusoidal depth profile. So you start shallow, and you get deeper, and then you go shallower again. I want to know what happens to those solutions. So essentially, you get a bifurcation, right? So if you're starting at very shallow depths, there's 3 solutions, 2 stable, 1 unstable. And then as you move to deeper water, this solution vanishes, and you just get 1. And then as you go shallower again, you're going to return on a different branch. Okay? You can flip it round and go from deep to shallow to deep. It's the same idea. But the important thing is that there's this critical moment where if you do the right thing, you can get on a fast branch, right? And then you can beat your competitors. So that's the idea. So just to show this cartoon basically takes 2 boats, one on the slow branch, one on the fast branch. When they race against each other, you see, obviously, the fast branch wins. They're both using the same amount of energy. It's just one gets themselves onto the faster branch at the critical moment. Okay, and if you do this in exactly the right way, you can calculate race times can be improved by a couple of % if you put in realistic parameter values. And that's the idea. So are there any questions about that? Yeah. I wish it was, but so basically I left Paris pretty much at the point where I got these results, and I never had time to implement them in the French team. So maybe I'll implement in the Irish team. So let's move on to the next part of the talk, which I mean really. So to answer that question more seriously, I really do think that there's a possibility to exploit this because, you know, experimentally you can measure this stationary point. So it's not an imaginary concept. It's really there. You really do have 2 solutions for the same cost. So yeah, I think the tricky thing in a rowing race is knowing exactly when that moment comes. Okay, so next I'll talk about this gunnel bobbing phenomenon, which turns out is kind of a popular summer activity in Canada. So I don't know, are there any Canadians in the room? Have you heard of gunnel bobbing? No, okay. So a collaborator of mine, Jerome Neufeld, who's at Cambridge, he goes gunnel bobbing every summer with his family. And essentially what they do is they go onto this lake and they try and push the canoe forwards just by jumping on it. And they have races and see who can go the fastest and so on. Okay, so a few years ago I was doing a postdoc with Jerome in Cambridge, and he showed me this video, and I thought it was brilliant. This is him gunnel bobbing. Okay, so that's all fun and everything, but I also thought this was kind of going back to the sports application. I was thinking this is kind of interesting from the perspective of canoe races. I don't know if any of you have seen an Olympic canoe race, but you really see that their bodies move up and down a lot during the race, and you can see the boat bouncing quite a bit. So this is from the Rio 2016 Games.
Last 250 meters, but look there at Sebastian Brendel retains his title in style. There's a silver for Brazil, very, very close for third indeed. It might
Yeah, so I mean, you can really see their bodies moving up and down, and the boat is really pitching and heaving a lot. So just to put in some numbers, you know, take the torso of Sebastian Brenzel and oscillate it at a frequency of 0.5 hertz. You can work out that the vertical force you get from that is around 60 newtons. If you compare that to the horizontal force of the drag, which is about 300 newtons, that's significant, right? You're talking about a significant amount of force which is injected vertically. So I was interested in understanding gunnel bobbing as a phenomenon itself, but also from the perspective of canoe races, whether the interaction between a boat bouncing on its wave field can be advantageous somehow. Clearly, you can push yourself forwards without a paddle. So if you're pushing yourself with a paddle, can you get anything extra from that? That's the idea. Yeah, so again, I put this picture of the ducks because really it's the same idea. Basically, you want to be pushing into positive surface gradients rather than negative surface gradients. First of all, I thought I'd mention, why is it called gunnel bobbing? So apparently it's an Old English word, gunnel, which is pronounced differently from how it's spelled. Essentially refers to the place where they used to prop guns on ships. So it's like a kind of gun wall, you can think of it. So illustrated here, and it's also illustrated on a sailing boat there. And bobbing just means bouncing up and down. So Jerome and his son, Miles, they set up some experiments a couple of summers ago, where they measured out the distance between two jetties, which was 25 meters, and then they got a stopwatch and an accelerometer on an iPhone. So the accelerometer data looks like this. Basically, you can get the frequencies of the oscillations, and you can work out that the gunnel bobbing can give you a range of speeds about 0.5 meter per second to about 1.25 meters per second. A range of frequencies, and this was attempted on a paddleboard and a canoe. So this is Jerome's son, Miles, on a paddleboard. So there's a few dimensionless parameters to talk about. First of all, I'll mention the dimensional parameters. So the key idea is if you're bouncing up and down in water, in deep water, the wave number, the approximate dominant wave number is set by the bouncing frequency squared over gravity. You can try it next time you go have a bath or go for a swim. And the phase velocity, you can also work out, is just g over omega. Okay, so those are two-dimensional quantities, and from those we can pull out some dimensionless parameters. So we've got the classic Froude number. We work out it's quite small, it's about 0.14. You can also work out a bouncing Froude number or an oscillating Froude number, which is the phase speed over square root GL. So it's the same idea as the classical Froude number, but with the phase speed instead of the boat speed. And from those, you can divide one by the other and get a Mach number. So that's kind of the Mach number tells you the boat speed with respect to the phase speed, and that's less than 1. So you can take gunnel bobbers from all over the world. So this is Jerome's son Miles. This is some guy I found on YouTube. This is me trying to do it in Oxford on a punt. A punt is kind of like a very long flat boat that people push around with a long stick. And this is Jerome in his college. And so you can take all. By the way, I'm not doing. It doesn't look like I'm doing very well, but actually, it's because the boat is so long that the speed is just quite small. The Froude number is decent, you know. Okay, so you can take all of these. Sorry, the colors come out strange here. You can take all these data points, and you can plot the two Froude numbers together. So this gives you an idea of the phase space. Basically, all of the data is kind of clustered around here, and the key thing is that the Mach number is less than 1. So the black dot here is the experiments Jerome did in Canada, and then all of the other dots are estimates I've taken from YouTube videos and so on. Okay, so you can interpret the x-axis. The higher you go on the x-axis, you're talking about low frequency oscillations, and the higher you on the y-axis is talking about high speed. And there's this sweet spot here where the data seems to lie. It's not clear exactly why that is, but what I would say is, if any of you have tried jumping up and down on a boat, you'll notice that it's difficult to do it at any frequency you want. So there's kind of a natural frequency that a boat has, and that relates basically, you can write down a linear dynamical equation, which just it's like a spring equation basically. So your spring constant depends on the boat shape and its derivative. And so really, like, the frequency that you can bounce at is probably just a function of the shape of the boat. So it's not clear that this is optimum. It might just be like what's possible, if you see what I'm saying. Okay, so that's the idea. I'll also mention, some of you might have looked at the Kelvin angle at some point. So the Kelvin angle is just under 20 degrees, and it's what you would see classically behind any boat or duck swimming in the water. Is this kind of classic Kelvin wake. So what we've got here is not a Kelvin wake. And the key thing to notice here, this is kind of like a Mach cone. So it's an information cone. You're creating some waves, but the source is moving. And so you've got this window, which can be drawn out by a triangle. So U is the boat speed, and CP is the phase speed. And if you trace out that triangle, you can work out a Mach angle, which is much larger than 20 degrees. Okay, there is likely a Kelvin wake somewhere in here, but it's not very big. So we can basically think of these waves as being irrelevant, and these waves being kind of dominant. Okay. What is the Kelvin angle? So the Kelvin angle basically is this. So like if you have a duck or something swimming in the water, it would produce these waves here, which you've got these like transverse waves, and then these waves, and then this angle here is about 19.5 degrees. And where it comes from, I think the Kelvin angle is something like, did I write it down? Oh yeah, it's the sine minus 1 of a third, and as far as I remember, it basically relates to the fact that the phase speed and the group speed are half of each other. And so that doesn't give 3. I realize that gives 2, but somehow when you draw the triangle, you get a 3. Does anyone know the answer to that question? It's quite tedious, right? But the key thing is the half, right? Yeah. So you have basically the group velocity, which is d omega dk, and you have Cp, which is omega over k, and omega squared is gk, and when you calculate Cg over Cp, you get 1/2, basically because of the square root, and that gives you this angle. Sorry, I realize that's not a proper explanation, but I can find a reference and send it to you. So these waves are really what we're seeing in this picture. It's not Kelvin waves, but these are waves sent out by a moving source. basically. So, okay, we tried to write down a simple model for describing this motion, and we thought about, okay, well, essentially what you're doing is you're forcing the water surface, and it's some combination of heaving and pitching. So heaving being up and down, pitching being like seesaw. It's not clear exactly what ratio they should have, so you can include an amplitude ratio of pitching to heaving, and you can also include a phase shift, right? So you can have heaving and pitching at different phases. And the idea is, can you sort of demonstrate theoretically that you can push yourself forward with that kind of pressure forcing? Okay, so mathematically, what do they look like? So heaving is just a function times e to the I omega t, take the imaginary part. What is that function? We can think of that function as being a translating Gaussian. So if I have a Gaussian pressure disturbance, I'm imagining that that's somewhat representative of a boat in the water, okay, which has some length scale and some width scale. And that Gaussian is translating at constant speed u. And it has some draft d. So the pressure, the cruising pressure, is rho gd times the Gaussian, which is cruising along like that. And then you can either oscillate it up and down, which gives you this pressure disturbance, or you can multiply it by x over L, which breaks the symmetry, and that gives you a seesaw. It's just a Gaussian times x, basically. This is kind of a proof of concept, like if you take these pressure disturbances, can we push ourselves forwards? And the simplest model you can write down, which is a non-dispersive model, we thought would be the wave equation. So what happens if you take the wave equation and you apply a pressure disturbance as a forcing term? Can you push yourself forwards with that pressure disturbance? So I recognize that deep water waves are dispersive, obviously, but just as a proof of concept, can you demonstrate forward motion even from a linear wave equation? So there's a few dimensionless parameters in the problem now. So there's the Froude numbers, the amplitude ratio phi, the phase ratio theta, and then two aspect ratios now, alpha and beta. Okay, this cartoon just shows like a solution of that equation. So you're just bouncing something up and down, and you're going to create some waves which propagate outwards. So this isn't entirely unrelated to fluid dynamics, of course. Does anyone know how you could derive this equation in the case of a fluid surface? In what context would you get that equation? Yeah, exactly. So this is exactly what you would get if you were in a shallow layer of water whose depth was 1 over k. That's exactly what you would get. And you can derive that. You can derive that pretty easily. So the idea is obviously in deep water this isn't going to apply, but we're going to use the kind of the shallow water analog to try and help us understand the problem. Okay, so how do we solve this? So the first thing you do is you apply a Lorentz transformation. So you're moving forwards at speed u, and you can move into that moving reference frame by applying a Lorentz transformation. Lorentz transformation has this very nice property of the wave equation. Does anyone know what that property is? If you apply Lorentz transformation to the wave equation. Does anyone know? So it's invariant, like you get the same equation. So it's quite nice because you preserve the equation that you started with, and the only thing you change is the forcing term on the right-hand side. Okay, so I apply my Lorentz transformation. I introduce this gamma parameter, which is defined up here, and then I seek a complex solution. So if I'm forcing it at some frequency, I expect my solution to be of this form, and then complex h bar satisfies the Helmholtz equation. Okay, so the Helmholtz equation with this forcing term on the right-hand side. So that's pretty easy to solve. You can solve it with the method of Green's functions. So if you know what pressure forcing you're applying, you can write down your solution just in terms of this integral. H01 is a Hankel function, so it's like a complex Bessel function, and P we know. So basically, you can calculate this numerically. Everything else is analytic up until this point, and then you have to calculate that integral numerically, and it will tell you what the wave field looks like. So, for example, in the case of a moving, heaving, pitching canoe, this is what the wave field looks like, and this is your Mach angle that you calculate. So that's what the theory shows us, and just to compare with the data that we observed, so you can trace out the Mach angle from photographs, and you can calculate the Mach angle theoretically, and they're roughly the same. They're both about 50 degrees. So that's reassuring. Another thing you can do is you can calculate the thrust force. So if you know your pressure and you know your wave field, then you can calculate the pressure resolved in the forward direction, which gives you a thrust. And for steady motion, you want your thrust to balance drag. And that happens for about a velocity of 1.5 meters a second, which is close to what we got in the data. So even this simple kind of non-dispersive model seems to capture the general behavior of this gunnel bobbing phenomenon. A couple of other things that were interesting is from this model you can prove that you must have both heaving and pitching to generate thrust. So if you just do heaving or if you just do pitching, you won't move anywhere. You've got to do both. And you can work out that the optimum parameters are equal proportion and out of phase. So that was, sorry? Yes. Very good question. Yeah. So that's like all instances of gunnel bobbing is with someone on the back of the boat. I have seen it done with 2 people, but then you could argue, well, one person's bouncing more than the other. Actually, we were quite interested in that problem theoretically, like what are the minimal conditions to break the symmetry? And I'll come back to that in a minute, because we revisited that. Okay, so the final part of the talk is about SurferBot. So SurferBot is basically gunnel bobbing on a really small scale. So this is some experiments that a friend of mine at Bristol did. And so he created this very small robot, which is 5 centimeters long. And it has this little asymmetric motor on it. And these oscillations create some capillary waves. And the SurferBot starts surfing on its capillary waves. So it's the same idea as gunnel bobbing, but just on a much smaller scale. And here you can see the SurferBot just cruising forward. I mean, why are we interested in this? Well, it's quite interesting for understanding how insects move around. So insects, which live on the water surface, they create capillary waves, and we're trying to understand if they're using those capillary waves to help push them around on the water. Okay, so this is SurferBot. I should mention again that this motor is slightly off-center, which goes back to your question. So if you put the motor just in the middle, it's not going to move forward. You've got to do something to break the symmetry. Okay, so now we're basically trying to revisit this, but properly. So using a dispersive model. When I say properly, I mean I'm still talking about potential flow rather than including, you know, vorticity and so on and so forth. But at least with a potential flow model, you can include the dispersion of the waves. So if you write down that potential model, this is quite similar to what Robin was talking about this morning. So you've got a Laplace equation for the potential in the fluid. And then you've got this raft, which is sitting on top of the fluid. The boundary condition of the raft is just that the water speed is equal to the raft speed. And then you've got this other boundary condition away from the raft, which looks kind of nasty, but basically what it is, so if you ignore these two terms, that's just classic deep water waves. So that's just kinematic plus dynamic boundary condition would give you those two terms. But you get an extra term due to surface tension, and you get another term if you include what's called like a weak viscosity. So this is something that people sometimes do. Obviously, potential flow is for inviscid fluid motion, but people include a weak viscosity term, which sort of represents the fact that these waves are decaying over some length scale and over some time scale. So I can send you some references if you're interested in that. And then you need some radiative boundary conditions as x goes to plus or minus infinity. Okay, so you can take this potential flow model, and the only subtlety here is you now need to couple it with the fluid-body interactions, right? So I can write down the fluid problem for the waves, but I also need to know what's happening to the raft. So I can take my raft, and all of this I'm just doing in 2 dimensions to make life simpler. So my raft, I'm allowing it to bounce up and down. I'm allowing it to pitch, and I'm assuming it's being forced by some force vector at a distance from the center. Okay, so I can write down the dynamics of the raft itself. So this is for linear motion, and that's for rotational motion. Okay, so basically, as this raft bounces around due to this forcing, which is represented by this vector capital F, you have a fluid response, so that's given by this pressure integral. You have drag, and you have gravity. Okay, so if you couple all of those equations together, the fluids equations and the raft equations, you can work out what the surfer bot is going to do. And this is what you get. So this was waves measured by measured in the experiments, and these are the waves that come out of the linear theory. And they also tracked the front and rear position of the surfer bot, and you can pull them out of the theory as well. So overall, we get quite a close comparison, which tells us that this is probably a fairly good model, and we can start to ask questions such as the one that you asked earlier. So, for example, with this model, you can now ask, what are the minimum requirements for generating forward motion? And one of the things we found is that you have to, by bouncing on one end of the raft, you will push it in the other direction, basically. So I haven't proved that mathematically, but from the numerics, it seems to be the case. That yeah, in the canoeing race, well, maybe we can go back and look at the video. But for the canoeing race, you could, if you wanted, you could modify other things, like you could change the weight distribution of the boat. Or if you have multiple people, you could change who goes in front, who goes behind. Yeah. So that's it, really. Oh yeah, one more thing I wanted to say, which is that essentially this phenomenon of wave-driven propulsion seems to happen across many scales, right? So this is an example of a honeybee that fell in the water. The honeybee falls in the water, it gets stuck, it can't fly away. What does it do? It starts flapping its wings, generates some waves, and it slowly moves towards the edge of the pool of water so it can climb out, dry its wings, and fly away. You can calculate some dimensionless numbers for the honeybee, so the two Froude numbers, the Reynolds number, and the Weber number. So the Weber number is like inertia to surface tension ratio. So essentially, we're saying that surface tension is very important here, all the way up to canoe gunnel bobbing, in which surface tension is irrelevant. The Reynolds number is massive, so we've really got everything from kind of capillary viscous flows to turbulent inertial flows, and at all scales, you've got this concept of creating waves and generating propulsion from those waves. So it would be nice to kind of create some sort of unified theory which encapsulates all of these different things, and just some very off-the-shelf, or sorry, off-the-press, hot off-the-press results, which I haven't published yet. But you can take a bunch of different propulsion examples. So everything from honeybees, surfer bots, some results of Longet-Higgins from the 60s using a plank of wood which is bouncing up and down, gunnel bobbing, also some fish that swim. So obviously they're not making waves, but they're generating vortices, and I wanted to also compare to them. So you can write down an approximate scaling of thrust due to oscillations. So if you've got some object which is oscillating, it's got an amplitude, a frequency, and a wave number, and you can work out an approximate thrust that you're generating. And you can work out an approximate drag associated with horizontal motion. And they collapse pretty nicely. So it seems that all of these examples have a thrust which scales something like this, balancing a drag that scales something like this. And so I'm not sure exactly what the conclusion from this is. Essentially, it seems that wave-driven propulsion and swimming are kind of hard to distinguish. They're both a way of turning oscillations into force. In one case, you're sending waves out backwards. In another case, you're sending vortices out backwards. There's some kind of efficiency, which is the ratio of the two, which is between about 0.1 and 10% efficient. So it seems like some of these things are doing better than others in the transfer of energy. But yeah, so this is still a work in progress. I'm trying to sort of figure out how to link these things up. But yeah, so if there are any questions, I'd be happy to answer them. Thank you.